Now we come to the type of titration that gives most new chemistry students the biggest problems. Here we have a weak acid. Acetic acid is a weak acid. We're going to be titrating it with a strong base, sodium hydroxide. And anytime you do a titration, something strong is involved. In this particular case, we're titrating a weak acid, which a lot of the time, for convenience sake, I'm just going to call HA, which is our designation for a monoprotic weak acid. And then we're titrating with a strong base. So this reaction is a big K reaction. It constantly generates products. It goes all the way. Why? Because we have a strong base, sodium hydroxide. It would also go all the way if, for instance, we had a weak base that I was titrating with a strong acid. Anytime one of the reactants is a strong base or a strong electrolyte, the reaction goes all the way. All right, so let's take a look at our titration. Now, initially, and this is just kind of a reminder, if I haven't added any of my strong base to my weak acid yet, all I have in solution is my weak acid. So my weak acid is just acetic acid, HC2H3O2, and since there's just a 1 molar concentration of that weak acid, I can do the calculation for the pH using my ice table, H plus C2H3O2 minus. Now, this is just a reminder of how to do these calculations, kind of a warm-up for what's going to go on later. So we have I, C, E, and this starts out at 0 for H plus, 0 for the acetate, the conjugate base of our weak acid, minus X, plus X, and plus X. Add the two lines up and we get 1.00 minus X, X, and X. Write our equilibrium constant expression as usual. So that's just going to be Ka is equal to H plus, and in this case I'm going to go ahead and use the generic A minus for acetate and HA for acetic acid. And then I just plug in my equilibrium constant for acetic acid, which is 1.8 times 10 to the minus 5 is equal, from my ice table, X times X, which is X squared. I'm going to assume that that X is small, so I'm not going to include it in my calculation, and so that's just going to be 1.00 molar. Solve for X, and when I solve for X, I wind up calculating the hydrogen ion concentration, which is simply equal to the square root of the Ka, which is 1.8, times 10 to the minus 5 times 1, and when I solve that, I get an X value that's equal to 4.24 times 10 to the minus 3, 4.24 times 10 to the minus 3. Take the negative log, that's the hydrogen ion concentration. Take the negative log and you get a pH of 2.372. So that's our starting place. That's just your warm-up. That's just to get you back into the swing of calculating the concentration of hydrogen ion in equilibrium with its weak acid and its conjugate weak base. All right, so now we're going to actually start the titration. And when we start the titration, here's what I want you to remember. We're actually adding, so if we started out with, let's say, 100 milliliters of solution volume, that's our weak acid HA, and I add 30 milliliters of strong base, my sodium hydroxide, if I add that to the solution, I'm going to have a new volume. And my new volume is going to be the 30 milliliters plus the 100 milliliters of weak acid. That gives me a new solution volume of 30 plus 100, or 130 milliliters. That dilutes my concentration of both sodium hydroxide and my weak acid, acetic acid. So if that's the case, I need to go ahead and do the dilution and come up with my new concentrations. So we're going to go ahead and do the dilution. So the dilution, in this case, for after we've added the 30 milliliters, will look like this. For my weak acid, acetic acid, and I'm just going to call that HA, it's going to be 100 milliliters of starting volume times its concentration, 1.00 molar, divided by the new solution volume of 130 milliliters. And that gives me a concentration for the acetic acid of 0.7692 molar. I'm going to do the same thing for the sodium hydroxide. And the sodium hydroxide started out at 30 milliliters. So that's going to be 30 milliliters of sodium hydroxide volume times 1.00 molar divided by my new volume of 130 milliliters. And when I do that calculation, I wind up with a new concentration for the sodium hydroxide of 0.2308 molar. All right, so now I have my new concentrations of both acetic acid and sodium hydroxide. The next thing that I need to do is the reaction. So the reaction, as I've illustrated above, is acetic acid reacting with the sodium hydroxide to form the product sodium acetate, which is the conjugate base of the acetic acid, and some water. So let's go ahead and write that. Reaction HC2 H3O2 plus NaOH goes to form NaC2 H3O2, and we're going to form some water. We're forming water because the hydroxide ion is reacting with the hydrogen ion from the acetic acid, and that gives you H2O. That's actually the driving force for a titration. Since this is a big K reaction, why is it big K? Because of the sodium hydroxide, the strong base. Anytime you have a strong base reacting with any acid, the reaction goes all the way to completion. So the table that we use when we have a big K reaction is the ICF table. My concentration of acetic acid is 0.7692 molar. My concentration of sodium hydroxide is 0.2308 molar. I start out with no sodium acetate, and I really don't care about any additional water. It's not going to make a difference. Since this reaction goes all the way, this is a limiting reactant problem, so we subtract whichever reactant is limiting. In this case, it's the sodium hydroxide at 0.2308 minus 0.2308, and every time 0.2308 molar of sodium hydroxide is used up, we make 0.2308 molar of the sodium acetate. I don't care about the water. So I add up my initial and my change lines, and what do I get? Well, first of all, my limiting reactant, the sodium hydroxide, is gone. My new concentration of acetic acid is 0.538 molar. My new concentration of sodium acetate is 0.2308 molar. All right, so you're at a special place in the titration. Well, it's a general space in the titration. And it's a very desirable space usually in the titration because quite often this is how we make what is known as a buffer. And a buffer is a solution that has a weak acid in the same solution with its conjugate weak base. And acetate ion is the conjugate base of acetic acid. We have a buffer. When you have a buffer system, you can either use an ice table to calculate the pH, or you can employ this special equation called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation says that the pH of this buffer will equal the negative log of the Ka, which we call the pKa, and the Ka for acetic acid is 1.8 times 10 to the minus 5. That's the pKa plus the log of the base over the acid concentration. Now, the base concentration is 0.2308 molar. The acid concentration of our buffer is 0.538 molar. And when we do that calculation using Henderson-Hasselbalch, we get a pH that's equal to 4.377. That's our pH for our buffer. Now remember, you can only use Henderson-Hasselbalch, HH, for a buffer. Don't try and use Henderson-Hasselbalch for anything other than a buffer pH calculation. Okay? Buffer, again, is where you have a weak acid in the same solution with its conjugate weak base. That's the only time you can use Henderson-Hasselbalch to solve for pH of your solution. Okay, so let's go a little bit further. Let's titrate to a very special place, and the very special place we're going to titrate to is called the equivalence point. So how do I know I'm going to the equivalence point? All right, so I'm going to add 100 milliliters of sodium hydroxide to my acetic acid solution. And what I note is that, well, I've got 100 milliliters of 1 molar weak acid acetic acid, and I'm adding 100 milliliters of 1 molar strong base sodium hydroxide. So if I have equal volumes and equal concentrations, that means I'm going to have equal number of moles of both. Let's go ahead and do the new volume just to show you. The new volume will be equal to 100 milliliters of sodium hydroxide plus 100 milliliters that's already in the pot of my acetic acid, and that gives me 200 milliliters total. My concentration for the sodium hydroxide is 1 molar. My concentration for the acetic acid is also 1 molar. Equal volumes, volume times the concentration equals moles. Equal volume, volume times the concentration, which is the same, equals moles. So that's going to give me the dilution if I look at it, and it'll be the same for both. So for both sodium hydroxide and for my acetic acid, these numbers are the same. I've got 200 milliliters total volume. I've got 100 milliliters of volume of each and the same concentration of sodium hydroxide and acetic acid. So that's going to give me 0.5 molar concentration for both my acetic acid and my sodium hydroxide. I write my reaction so that I understand what the chemistry is. If you don't understand the chemistry, then the math doesn't really matter. You're just going to get led down the wrong path. The sodium hydroxide combines with the acetic acid to give me sodium acetate, NaC2H3O2 plus H2O. Because of the strong base, this is a big K reaction. It goes all the way. So it's an ICF table. I have 0.5 molar concentration of acetic acid, 0.5 molar concentration of sodium hydroxide. I don't start out with any products, but this reaction is going all the way. So it's minus 0.500, minus 0.500, and plus 0.500. All right, so after everything is reacted, what do I have left? I don't have any acetic acid, I don't have any sodium hydroxide, but I have a 0.500 molar concentration of the basic salt. And all I really care about, I don't really care about the sodium cation, because you know that that doesn't hydrolyze water. But this acetate is the conjugate weak base of acetic acid. It is a base. It's a weak base, and it will hydrolyze water, and it will affect the pH of my solution. So I'm going to go ahead and calculate the pH of the solution using the weak base. Now, if you don't get this, you're not going to get the correct answer. Since this is a base, C2H3O2 minus, I have to do the water hydrolysis. And this is an equilibrium reaction. The acetate ion, to some small degree, is going to grab a proton from water, make a little bit of its conjugate weak acid, and every time it takes a proton from water, it leaves behind a little bit of its conjugate weak base. Now notice, this is an equilibrium reaction. Because it's an equilibrium reaction, it doesn't go all the way to products. It's an ionization reaction that barely happens, so we have to use an ice table. I can't use the Henderson-Hasselbalch equation to solve for this because I don't have any of my acid. I can only use Henderson-Hasselbalch for a buffer, and just having weak base salt in water is not a buffer. So my concentration of acetate is 0.500 molar. I start out with no acetic acid, no hydroxide ion, but now the reaction proceeds to equilibrium, and that's a minus X plus X plus X, and at equilibrium I have 0.500 minus X and X and X for my hydroxide. So now I want to write my equilibrium constant expression. Well, this is a weak base, not a weak acid. So my equilibrium constant expression is going to be a KB expression. As a KB expression, I go ahead and plug in my products. I'm going to go ahead and use the generic HA, just to make it a little easier on myself, times hydroxide ion. These are my two products of this equilibrium reaction, divided by my acetate, which I'm just going to call A minus, so I don't have to write C2H3O2 minus. Now I need a KB. Well, I need you to remember that Ka times Kb equals Kw. So you're going to get the Kb by taking Kw, 1 times 10 to the minus 14, that'll be on the front cover of your exam, don't forget that, divided by the Ka, which was given for acetic acid of 1.8 times 10 to the minus 10. and we get a Kb that's equal to, so Kb of 5.6 times 10 to the minus, I made a mistake over here. This is 1.8 times 10 to the minus 5. My apologies. And that gives us a Kb of 5.6 times 10 to the minus 10. So I'm going to go ahead and plug that in and solve for what? I'm going to solve for the OH concentration. So this will be 5.6 times 10 to the minus 10 is equal to x times x, which is x squared, divided by, and again I'm assuming that that x is small, divided by 0.500. I solve for x, and x is equal to the hydroxide ion concentration, which is equal to the square root of the Kb, 5.6 times 10 to the minus 10 times my base concentration, 0.500 molar. I get a hydroxide ion concentration that's equal to 1.67 times 10 to the minus 5 molar. And that's in hydroxide ion. I'm going to go ahead and take the negative log of that, and when I take the negative log of the hydroxide ion concentration, I get the POH. The POH is 4.778, and to get the pH, I simply subtract the POH from 14, which is the pKw, minus 4.778, and that's equal to 9.222. And that's the pH of my solution at the equivalence point. Why is the pH basic at the equivalence point of titrating a weak acid with a strong base? It is basic because at the equivalence point, I don't have any weak acid, I don't have any strong base, but I do have weak base. So when titrating a weak acid with a strong base to the equivalence point, you have a basic salt. In this case, sodium acetate is my basic salt, which gives me a slightly basic pH. Not hugely basic, but it is definitely greater than 7, and so it's basic. Now we come to the last titration in this series. We're actually going to add 101 milliliters of sodium hydroxide. So that's going to be a greater volume of sodium hydroxide than we have volume of equal concentration of acetic acid. So we're actually going past the equivalence point with the addition of 101 milliliters of sodium hydroxide. So we're going past the equivalence point. So we expect our solution to be very basic. If your calculation doesn't validate that, then you've done something wrong. So our new volume for this calculation will be equal to the 101 milliliters of sodium hydroxide that we're adding to 100 milliliters of our weak acid, acetic acid, for a total solution volume of 201 milliliters. So let's go ahead and do our dilution. See what our concentrations are after we add that 101 milliliters. For the acetic acid, the dilution is 100 milliliters times the 1 molar concentration divided by 201 milliliters new solution volume. And when we do that, we get for HA 0.4975 molar concentration. We'll do the same thing for the sodium hydroxide. And for the sodium hydroxide, the dilution looks like 101 milliliters times our 1 molar concentration divided by 201 milliliters solution volume. And that's going to give us 0.5025 molar concentration. All right, so here are new concentrations of the weak acid and the strong base, sodium hydroxide. Let's go ahead and write our reaction, which is going to be HC2H3O2 plus the sodium hydroxide. And that is going to react completely to form NaC2H3O2, and it'll make some water. Same thing what we've been doing all along. This is a big K reaction. Just reminding you, it's big K because of the presence of the strong base. So it's an ICF table. ICF, we've got 0.4975, sorry about that, and 0.5025 molar of our sodium hydroxide. I don't have any sodium acetate, I don't have any water. My limiting reactant now, you notice, is my weak acid. I have an excess of strong base. So we're going to go ahead and subtract the limiting reactant from both sides. 0.4975, that's a 7 by the way, 0.4975 minus 0.4975, and every time we lose 0.4975 of our acetic acid and 0.4975 our sodium hydroxide, we make 0.4975 molar of our sodium acetate, our conjugate weak base. We also make a little bit of water, but we don't care. So let's go ahead and add up our initial and our change line. We're going to have 0.4975 molar of our sodium acetate. When we subtract 0.4975 from 0.5025, we get approximately 5.0 times 10 to the minus 3 molar in sodium hydroxide, and we have no acetic acid left. So I have two things left in solution. I have strong base in the concentration of 5 times 10 to the minus 3 molar, and I have 0.4975 molar concentration of my basic salt. So the question is, how do you calculate the pH of this solution? What matters in this solution? Well, the truth is that this base, acetic or acetate ion, is such a weak base that it's going to have no impact on the pH of the solution if there is excess strong base. So the answer is we get the pOH directly from the concentration only of the strong base when strong base is in excess. So when the strong base is in excess, calculate the pOH based only on the concentration of the strong base. And I'll show you something that might help you understand exactly why that is the case in a moment. So take the negative log of 5 times 10 to the minus 3. And when you take the negative log of 5 times 10 to the minus 3, you get 2.301. That's the pOH. We're going to get the pH by subtracting the pOH from 14, which is the pKW at 25 degrees Celsius. So when we subtract 2.301, we wind up with 11.699. 11.699. And that is the pH of this very basic solution. So let's see if we can understand why the conjugate weak base doesn't make a difference when we have excess strong base. If you were to do, first of all, how is it that the weak base actually could cause a solution of water to become basic in the first place? Well, this is the reaction that we did at the equivalence point. And that's through the hydrolysis of water by the weak base. And it hydrolyzes water to produce HC2H3O2 plus some hydroxide ion. Well, if you think in terms of Le Chatelier's principle for this equilibrium reaction, we actually have, because of the strong base, a 5.0 times 10 to the minus 3 molar concentration initially of our hydroxide ion. And even though we have a 0.4975 molar concentration of weak base, the presence of this excess amount of product. So this didn't start out at 0. It started out at a pretty hefty 5 times 10 to the minus 3 molar concentration of hydroxide ion. And what does Le Chatelier's principle suggest if we add in product, which this is in the base hydrolysis reaction? It suggests that the reaction is going to shift in the direction toward the reactant side because of all this excess product. So when we have strong base, this is strong base, it moves the reaction, it shifts it toward the reactant side, and what it does is it minimizes to an extraordinarily small degree the ability of this weak base to hydrolyze water to produce any more hydroxide ion. So it's not going to make any difference. So it doesn't really matter what the concentration of the weak base is. Its Kb is so small that the only thing that matters is the excess strong base concentration. So we get the POH by taking the negative log of the excess strong base once we've gone past the equivalence point, and then we subtract it from 14 to get the pH.